Hello! In the previous chapter we learned that with the t-test we can compare two means. However, using the t-test we cannot compare more than two means and we can only use one independent variable or factor. But for comparing means of more than two groups and manipulating more than one independent variable, we use a statistical test called ANOVA or analysis of variance. In order to conduct the ANOVA test, we have to have a metric dependent variable, so it has to be measured at an interval or ratio level, and our independent variables or variable or factors have to be categorical. We have two types of ANOVA tests based on the number of independent factors, and the first one is called one-way ANOVA, and this one is used when there is only one categorical variable or factor, and the second one is called n-way ANOVA, and this is used when we have two or more factors. In this tutorial we will focus on one-way ANOVA, and then there will be a separate one on the n-way ANOVA. The null hypothesis for the one-way ANOVA is typically that all means are equal. Let's have a look at the example we will use. You are a marketing manager at an online fashion store and you want to analyze the effect of online promotion on sales. And you conduct an experiment and select a sample of 30 comparable products to be included in the experiment. And then you randomly assign these products to one of the three groups, and that's either high promotion level or medium promotion level or low promotion level. And you record the sales over one day, and this means that you have 10 products assigned to each treatment. We want to find out if the price promotion influences sales of the products. Okay, let's go to RStudio now. First of all, we will load the data using the read.table command. Let's do this. And now we will have a look at the data frame so that we have an idea what we are going to work with. We have the observations in the first column, the promotion level denoted by number 1, 2, 3 in the second column, and then we have a variable called newsletter, which we will not use in this example, and the last column is sales, which is our dependent variable. So this is the data we will work with. Now let's go back to the script, and what we will do now is that we will convert a grouping variable promotion to factor using this factor function, and we will name our levels of promotions here as high, medium and low. Let's run this. Let's inspect the data now. First we will use the function str or structure to get a quick overview of our data frame. And in the output we can see the number of observations, number of variables and the type of variables. Then we ask R to display the whole dataset using the function print, which will print the value of an object, so in our case the whole online store promo dataset. So we can see our whole dataset here. And now to get a first impression if there are any differences in sales across the experimental groups, we will use the describe by function from the psych package. But first we will have to load the package which we have in the library, so let's load it. And now we ask R to display basic summary statistics by our grouping variable promotion. Perfect, so you have here group high, group median, group low, and for each of them you can see, for example, sample size, mean, standard deviation, median, and so on and so on. We can now visualize the data using the plot of means. First of all, we will load libraries Plier and ggplot. And now we will create a graph using ggplot function, which we can see here. First of all, we specify the data set, so the online promo, online store promo, and the variables we will use, which will be promotion and sales. And in the next layer, we will use the summary function, stat summary. And since we want to get the mean of sales displayed in our graph, we will use the argument fun dot y equals to mean, and the argument gem equals to bar will display values as bars. We also want to add error bars. We will add them using comma_stat_summary again, and we will use an argument fun.data equals to mean CL normal, which will add a standard 95% confidence interval while assuming normality. And to add this in the form of point range geom, we will add the geom equals to point range argument. Finally, we add labels and format the graph. Okay, we can run this. Let's wait for a second. Let's wait for the graph. Perfect. So we have high group, medium group, and low group or promotion level. Here we have sales on the y-axis, and from the graph we can already see that the mean sales of the high promotion products are the highest, whereas mean sales of low promotion group are the lowest. So let's go back to understanding what the ANOVA will do for us. ANOVA tests for an overall difference between groups of promotion levels, and if the test is significant, it tells us that the group means, which are in our case sales under different promotion levels, are different. However, it doesn't tell us exactly which means are different. And to find out where exactly the differences are and between which groups, we will have to conduct the so-called post hoc tests. Post hoc tests take every pair of groups and perform a test on each pair, and hence we will look at the post hoc test only in case our ANOVA is significant. And the basic concept of ANOVA is the decomposition of the variance in the data, where we have to consider three components. The first one is the variability between scores, so the total sum of squares. Then the variability that can be explained by the model, or how much variability there is due to the experimental manipulation, and this is model sum of squares. And the third, how much cannot be explained, how much variability is due to individual differences in performance, which is the residual sum of squares. The F statistic which we use for ANOVA compares the amount of systematic variance in the data to the amount of unsystematic variance, and we then compare the calculated F statistic to the critical value and decide if the null hypothesis can be rejected or not. Before we can conduct the ANOVA in R, we have to check if all necessary assumptions are fulfilled. But there is a separate tutorial on the assumptions for ANOVA, so in case you want to learn this, please watch this tutorial. And for our data, all assumptions have been fulfilled, therefore we can directly continue with the ANOVA test in R. Okay, we will use a function AOV, and we will assign the results of the test to the object of the same name, as you can see here. And as usually, the dependent variable comes first, then we have the tilde sign, then we have the independent variable, in our case promotion, and then last but not least we specify the data set that we will be using, in our case online store promo. Let's run this command. This is performing the ANOVA test now, and using function summary we can ask R to display the output from the test, which we can see down here. Let's have a look at it. In the output we can see the degrees of freedom, sum of squares, mean square, F statistic, and the most important thing for us is the probability. Since the p-value is significant and lower than 0.05, we can reject the null hypothesis of equal means within our three levels of promotion, and if this null hypothesis is rejected, then we can conclude that there is a significant difference between the mean sales of the three promotion groups. Okay, let's go back to the R script, and we will now compute the effect size, or the so-called eta squared. Eta squared, or effect size, measures the variation in the dependent variable that is explained by the independent variable, and we can extract the relevant sum of squares from the list to calculate from our list AOV, which we can see here on the right side. And to calculate the effect size, we have to divide model sum of squares by the total sum of squares. And what we do in this command is that we take the model sum of squares, which is this part, so the variance explained by the model, and divide it by sum of model squares, or model sum of squares, and residual sum of squares, which is actually, this sum of these two is actually the total sum of squares. And if we run this command, then we get the result of the eta squared, or the value of eta squared. We could now report the results from ANOVA in the following way: that there was a significant effect of promotion on sales levels. We report the F statistic, the probability value, and the eta squared. But remember that this doesn't tell us where the differences between groups lie, and to find out which group means exactly differ, we need to use the post hoc procedure, so let's have a look at them. But before we do that, I have one more note on the assumptions. The AOV function also automatically generates some plots that you can use to judge if the model assumptions are met. These are also described in the tutorial assumptions for ANOVA. Okay, let's come back to the post hoc test now. So by rejecting the null hypothesis, we concluded that there are significant differences between means of groups. However, we still don't know where the differences between groups lie exactly. Post hoc tests will help us to find this. So what are these post hoc tests actually? They consist of pairwise comparisons that are designed to compare all different combinations of the treatment group, while also correcting the level of significance for each test so that the overall type 1 error remains 0.05. So they take every pair of groups and perform a t-test on each pair. There are several post hoc tests, but we will have a look only at two of them, and this will be Taki, HSD, and Bonferroni tests. These both control for family-wise error, and the Bonferroni test tends to have more power when the number of comparisons is small, whereas Taki HSD is more powerful when comparing large numbers of means. So in other words, we rejected a null hypothesis that our means are equal, and now we would like to test each of the pairs separately. So this will be our null hypothesis now. Okay, let's first implement the Bonferroni procedure in R using the pairwise.t.test function. Again, we first specify the dependent variable, which is the sales, and the independent variable comes then, which is the promotion, that we specify the data set online store promo, and the last argument p.adjust.method will specify the type of the post hoc test we want to run. So in this case, Bonferroni. Let's run this command, and what we are looking at now are the probability numbers in the small table here in the middle. We can see that the probability for each of the tests is lower than 0.05, all three of these numbers in the table. So we can reject the AH0 or the null hypothesis, which says that the means are equal for all three tests. That means that they are different. And to compute Taki's HSD, we will come back here, and we will use the function glht from the multcom package. So first of all, we will load the package, and then we will run the test using this function glht and assign the results to an object called Taki's. We specify the model we will run the test for, and then we use the length CT argument, which will always equal MCP for ANOVA. And then we have the independent variable equal sign and the name of the test in quotation marks. So this is how the function for running the Taki's test, Taki's HSD test should look like. Let's run it. And using summary function, we ask for the results from the Taki test. In the output, we can again see a table where we have three tests. It's here. First column shows the estimated difference between the two groups. And as you can see in the last column, we have the probability. And all the results are significant. So we can again reject the null hypothesis, which says that the means are equal for all three tests. And we can also very easily ask R to provide confidence intervals by running this conf_int Taki's, and we can also plot them So let's ask for this. And you can see that the confidence intervals do not cross 0, which is here on the right side, which means that the true difference between group means is unlikely to be 0. And at the end we should report the results from the post hoc test, and we could state something like this. The post hoc test based on Bonferroni and Takis HSD revealed that cells were significantly higher when using medium versus low levels, high versus medium levels, and as well as high versus low levels of promotion, so basically all three combinations. That's it for one-way ANOVA. Thank you for watching the tutorial.